I introduce myself. My name is Singh Matharu. First name is long, that's the G, and I work for the US Nuclear Regulatory Commission. Am I still sharing?
Yes, you're sharing.
Okay. So we're going to talk about electromagnetic pulse and geomagnetic storms if we have time. And please keep the time for me because I cannot see anything else but my slides. So what happens if you explode a nuclear bomb high in the environment? You get a lot of gamma rays. You're going to damage a lot of equipment without causing actual damage to the property itself, in the sense that you don't get a destruction like we saw at Hiroshima. What's happened in the past? The Soviet Union did an explosion above Kazakhstan back in 1960s, and what they found was they could disrupt a lot of electrical electronic equipment. Transmission lines were affected, radio communications were affected, satellites were affected, power supplies, communication systems, anything that got electrical in it was disrupted. And just not to be left behind, the US did something similar back in 1962, and they exploded a nuclear bomb above Johnston Island, which is about 800 miles from Hawaii. And very similar results. They could adversely impact transmitters, military radios, streetlights, cables, and all kinds of electronic equipment that's in the vicinity, or up to about 800 miles, I should say, not even in the vicinity of the plant. So what was the magnitude of these tests? The Starfish prime, as they called it back in 62, was about 1.44 megaton burst, 250 miles above Johnston Island in the South Pacific. And the strength of the wave was about 5.6 kilovolts per meter. The USSR test back in 1960 was a 300 kiloton burst, about 180 miles above Kazakhstan, about 1,000 to 1,300 nanotesla per minute E3 pulse. And I'll describe what E1 and E3 is a little bit further on. And what they found was they could disrupt power plants, and they could also disrupt a lot of electronic equipment. So what are we going to talk about? We're going to talk about the overall reactor fleet that we have in the US. I'll give you a big picture. We'll talk about the long-term grid loss because of the EMP. We looked at what would happen to a nuclear power plant in the US. It's a qualitative discussion rather than a detailed, significant research effort. There's some ongoing research, some mitigating strategies, and if I have time, I'll go through solar storms. On the right-hand side, what you see is a picture of what would be an explosion. We call this a smile diagram because right in the middle here, if the explosion is almost to the north of northern part of the United States, the maximum impact is the red line, which is like the lips of a smile, and the blue is the most vulnerable area, and the light blue would be also affected. So you can see a significant impact area for one explosion. The reason for the smile is because of the interaction of the electromagnetic waves with the electric field, geomagnetic field of the Earth and the gravity. So what is EMP? There are two types, right? One is the man-made. We just discussed about the man-made, and the natural, which is what Kevin almost introduced to us, which is a geomagnetic storm. So what do we get from EMP is a burst of electromagnetic radiation resulting from a suddenly fluctuating magnetic field. So a nuclear bomb detonated hundreds of kilometers above Earth's surface is known as a high altitude electromagnetic pulse, or HEMP, not the drug, but the electrical kind. A geomagnetic storm caused by the coronal magnetic eruptions, the CMEs, with solar flares can create a long duration pulse that can burn out utility power transformers and cause widespread power outages. Now, NRC, which is US Nuclear Regulatory Commission, we've been doing research on the EMPs for quite some time. Back in '83, we looked at what could happen and whether we could achieve safe shutdown. We are also looking at we had generic issues on the evaluation of GICs, and this is ongoing effort. And Kevin, you may be able to support us with your CISNI and the other work that you're doing. Like we said, the high altitude detonation of a nuclear weapon can generate a large EMP. It has three components: E1, E2, E3, and there is a difference in the quality of the three waves. E1 and E2 refer to the nearly instantaneous emissions that are most commonly associated with the HEM. E1 and E2 can result in damage to electronic equipment and low medium voltage infrastructure, electrical infrastructure. E3 or the magnetohydrodynamic EMP pulse can drive low frequency GIC type of currents in the transmission lines and power transformers. So E3 is very similar to a GIC. So there's a lot of commonality there. And the E3 waveform is a long duration pulse lasting for hundreds of seconds. And what it does is it induces current in long power lines and communication lines, and it destabilizes the equipment such as transformers. And E3 wave effects are, E3 is very similar to the solar geomagnetic effects. So E1, a little bit more detail on E1. Very fast component of the nuclear EMP. It is too fast for ordinary lightning protectors and destroys computers and communications equipment. Too fast. It's gamma rays, essentially. E2 pulse, many similarities to pulses produced by lightning. So it's least dangerous type of EMP because of the widespread use of lightning protection. So we are familiar with E2 type of pulses. E3, which is a much slower pulse caused by the Earth's magnetic field being pushed out of the way by the nuclear explosion or solar storm, followed by the field being restored to its natural place. This process can produce geomagnetically induced currents in non-electrical conductors like power lines, which can damage or destroy power line transformers. E1 pulse travels at about 90% speed of the light, peaks after about 5 to 10 nanoseconds, and it's over in about 1 microsecond. Obviously, our circuit breakers are not fast enough to protect us from that. Circuit boards, electronic circuit boards are sensitive, and potentially we can damage integrated circuits. And cables can overheat and give us false readings in our instrumentation and control systems. In the transmission systems, the SCADA, as we call it, supervisory control and data acquisition systems, they are vulnerable because it's mostly electronic and we use them all over the place. We use them in our nuclear power plants, the transmission systems, water management, oil and gas pipelines throughout the country. And what we found is that by testing, electronics can experience up to about 700 amps during the E1 pulse. So it's a significant jolt to the system. Like I said, E2 is very similar to the lightning, and lightning protection probably protects us from E2 type of waves. But just note that E1 could partially damage lightning protection systems, and then E2 could result in more damage. E3 pulse lasts from tens of seconds to several minutes. It produces a direct current similar to the GIC. And if you've done some research on GIC, you know what to expect. Transmission lines, transformers are vulnerable. Typically, it's an overheating issue. All right, so what do we have in the US? We have about 100 boiling and pressurized water reactors. We produce about 20% of the electric power. We've got two new AP1000s, which is a passive type of design. And we've got one small modular reactor design under review. I should say it's now been reviewed and licensed. Construction has not started yet. Overall, what are we looking at? We're looking at the offsite source, which is the grid affecting us. We're looking at transformers. We're looking at the impact on the main generator and possibly looking at the cooling water systems. And then inside the reactor vessel, we're looking at instrumentation and control systems that we need to monitor the vessel itself. So what's the big picture? We feel the nuclear power plants would achieve safe shutdown following an EMP event. We feel there's a core cooling capability and spent fuel cooling capability will be required indefinitely, but we feel it'll be there. We would need long-term logistics support for safe shutdown, and we are evaluating other experiences nationally and internationally. So we know that all nuclear power plants are designed for safe shutdown following a total loss of transmission system or offsite power. Like I said, we have a reasonable level of confidence that safety systems required for plant shutdown and extended core cooling functions will be available post EMP event. We feel or we know we need to have the emergency diesel generators available. They must continue to function. And what we also know from our past operating experiences, maximum outages we've suffered in the US is about 14 days of loss of offsite power. In the terms of hemp, it could be longer. So need to evaluate long-term core cooling functions. We have some on-site fuel oil for the diesels, and we know it's limited. We also know that diesel generators are robust. They are not usually operating, and we expect them to survive during an EMP event. Post Fukushima, we've installed auxiliary equipment. We've managed to extend the battery life. We've got other pumps and diesel generators. Some of them are portable that we can secure from remote locations and help safe shutdown of the plant if needed. And we also have, in the US at least, almost all operators have commercial arrangements for resupply of diesel fuel oil if and when needed. So, like I said, what we need for extended duration, we need to make sure we have enough fuel oil, lube oil, treated water we may need at some point. We need to arrange for personnel, operators, mechanics, maintenance staff, and we also need to maintain plant safety and security during this extended loss of offsite power. What's the design basis of the nuclear power plants? Typical, right? We know we have the capability for safely shutting down given the loss of offsite power. We know we can maintain safe shutdown conditions given total loss of on-site and off-site power for at least 4 hours. In other words, if the diesel is somewhat EDG, somewhat reluctant to start, or damage that can be repaired, we can last 4 to 6 hours to 7 hours without AC power. We also know that the equipment required for safe shutdown of the plant is usually not connected, and that's important. And you should be able to withstand the external event. And again, we do not rely on non-safety equipment that could be exposed to the EMP. Typical structure of a nuclear power plant, and I'll describe a little bit more detail. The containment has got a liner, which is a good shield. There's an annulus and a very thick concrete structure on the outside. And then the auxiliary buildings or safeguard buildings is again concrete, a lot of barriers, a lot of equipment. And similar to the fuel handling building, has got a lot of concrete, a lot of steel, which acts as a barrier for EMP. Like I said, the containment design, up to 2-inch steel liner, 3-foot annulus, and 3 to 4 foot thick reinforced concrete structure. The auxiliary building, although it's not designed to withstand the high pressure that you get from the steel liner, that you need for the containment, it's still fairly heavily reinforced. It's concrete structure, and the equipment itself is in rooms which have got concrete walls and doors. So we expect that the gamma ray that we get from the E1 wave will be somewhat attenuated. The fuel pool building, which is another issue that we experienced, we had problems at Fukushima, we feel is also adequately protected because of steel in the concrete. So typical nuclear power plant design, connected at 230 kV to the grid system. We have the breakers that isolate the plant from the grid, the generators, and we have the transformers that are all connected to the grid and perhaps vulnerable to E1 because they're outside, E2 because of the lightning effect that can strike on the transmission lines, and E3 because of the connection to the long transmission lines. So the equipment that we are interested in is the interface between the grid and the nuclear power plant. All that is exposed to the EMP wave. So what did we think? We assume that the E1 wave lasts a few nanoseconds, decays quickly. We expect that E1 and E2 voltages cause breakdown and flashover paths within the power off system. And we expect E3 to damage the equipment that's connected to the long transmission lines. And that's basically our transformers. So we assume the loss of offsite power and we damage all non-safety equipment. In other words, all our relays are gone, all our protective functions are gone, breakers don't function. Maybe we damage the main generators, and breakers and turbine systems, electric systems do not function. However, we do expect mechanical systems to function. We do not rely on automatic digital and analog control and instrumentation systems because they're mostly associated with power production. We are interested in safely shutting the plant down. Oops, too many slides. Okay, so what happens to the nuclear power plant? We expect the generator trip on overspeed. All the other trips have failed. When the generator trips, you're going to get a reactor trip. And the control rods insert. We expect the primary and the secondary system pressures to increase and automatic actuation of injection systems. Now, the automatic actuation may or may not take place, but irrespective, if they don't, we can take manual actions. We feel the diesel generators will start and run because they were not connected to the electrical power system before the event. And again, most of the safety systems are not connected to the external power sources. And that's important because the E3 wave, which travels through the conductors, through the offsite sources, through the transformers, can carry into the plant, can damage equipment that's connected. But most of the standby systems that are required for safely shutting down the plant are not connected electrically. We also know that safety systems are designed to fail safe. In other words, if you lose power, the device will fail into a safe mode. Automatic actions that we need are critical for large breaks in the nuclear power system. We do not expect any line breaks. We do not expect any accident conditions just because EMP event occurred. We have time to take manual actions. So the EMP signal may get into the plant interior again because it's connected to the external cables. It can interact with the power grid and induce currents and damage our instrumentation. I think my two bullets are repeated, right? The first two bullets are repeated. I'll fix that. Like I said, we
5 more minutes.
Oh, how many? I'm sorry?
5 more minutes.
Okay, I'll zip through this. We do not expect severe damage. We expect the equipment to survive, and we expect to safely shut the plant down because everything is in isolated mode. There are some critical equipment that's usually running, cooling water is running, HVAC systems are running, and because they're connected to the external systems, there could be some challenges there. We do not expect the reactor side to have any impact because of, or any reverse impact because of the EMP. Spent fuel pools, like I said, we do not expect any damage there. They're protected by concrete walls, reinforced concrete walls, and the metal and the reinforcement attenuates the EMP wave. And again, we have time to manually initiate fuel pool cooling if needed. We also have an option of dry cask storage, and because there's no electrical system required, we feel dry cask storage systems are fairly safe. So what is it about the electrical design that's saving us? We know the cables are run in raceways which are metallic. We know cables have shielding. We know that there are concrete walls. So because of all these built-in features which were not designed for EMP, we feel the EMP wave will be attenuated. And these types of cables, we all familiar with types of cables. Most of them are shielded. The shielding helps us in reducing the induced currents in the cables. Therefore, we expect to diffuse the damage that can potentially occur. There's some research done by EPRI. EPRI is a private industry research lab. And this report is available on the internet if you want to see what the effects were. They did some research on what can happen. SCADA systems, control centers, insulation flashovers. They found some damage. They also expected a lot of equipment to survive. This is an incomplete report. This is just a preliminary report. Like I said, it's available on the internet if there's more interest in that. They are continuing to do their research. They're looking at switchyards, they're looking at substations to look at the impact of E1, E2, E3. And what they found is, like I said, some of the equipment, there's some damage, but they expect a lot of the systems in the substation to survive. The E2 wave, they do not expect any damage. And E3, they feel there might be a voltage collapse in the system because of the failure of transformers. So mitigation, how do we mitigate? Surge suppression devices and filters. We need shielding. We need grounding. We need better cages, as they call Faraday cages, for equipment that we feel must survive. Based on, like I said, to summarize, based on industry research and transformer experts, we do not expect a catastrophic failure of large transformers. We do expect some to fail. We do not expect all to fail. We feel the non-safety systems in the nuclear power plants need to be evaluated. We've not done that yet. And the introduction of digital controls in non-safety systems and safety systems need to be looked at further. Where do you find some standards? Military standards in the US, they provide good source of how to strengthen, harden equipment. Like I said, shielding, grounding, filtering, and surge protection are ways that we're looking at. And pictures of what hardening looks like, shielding. And again, we know what the nuclear weapons are, we know how they detonate, we know what type of electronic waves that they generate. So we can mitigate all that if you have to spend money though. We can also test and we can harden equipment. Solar storms, like we said, I don't have time, but I'll put the slides up. Kevin, it's basically the similar discussion, talks about geomagnetic storms, talks about what kind of currents we have seen. If you're familiar with the 1989 event, and I think most people in Sweden would remember it because these are all the events. On October 31st, the sunstorm caused problems for the Swedish power system. I think you lost about 7 or 8 500 kV lines, and we tripped some nuclear power plants. And in Canada, Hydro-Quebec system collapsed on us. So we've been looking at the impact of solar storms, and I've got a bunch of slides on those. I've got a transformer damage picture. This was a nuclear power plant in Northeast. On the left-hand side, I've got the winding of a new transformer. On the right-hand side is what happened to this transformer after a solar storm. And I've got a discussion on how to harden power grids. from solar storms. And again, for the nuclear power plants, we've got some mitigation strategies, how to reduce the loads on the transformers, because in this case, we do have a warning of a solar storm approaching. We know the GICs are going to be generated. The nuclear power plants can take action. We feel the grid operator can take action to at least limit some of the damage. That is a quick summary of my solar storms.